So far in this lecture series on the Inf-sup condition, we focused quite a bit on the theory part, and in this video I'd like to shift attention a little bit to the practice. And in this case, practice means simulation results. And what I would like to show you is that we really have to know what we're doing in order to get good simulation results when our problems are no longer coercive, but rather we have to rely on this Inf-sup condition. And I'll show you these results for two benchmark problems, two relatively simple problems. And I'll also show you an example that is a bit more complex, a bit more engineering practice relevant. Because of course that's the objective of this course, to make you aware that the finite element method is really not just a black box method that you can throw against any problem and it will give you a good solution. No, we have to really be careful. We have to know what we're doing. And for some problems, like the problems that we're dealing with in fluid mechanics, we really do have to know what we're doing, and it's really not so trivial. So before I show you those simulation results, I first want to kind of rehearse the difference between coercivity and Inf-sup from a discretization perspective, because so far I haven't really talked much about the discretization. Everything that I've talked about applies in the infinite dimensional setting, right? And that means that our function spaces v, or here in the bottom x and y, that those are infinite dimensional, that there are infinitely many functions in there. Now the same analysis tools apply also for the finite dimensional setting, a finite element method, where we only have a select few number of functions in these spaces. So the same analysis applies, but we haven't talked much about that yet. And now that's actually going to become important. And I think I may have addressed this once or twice before, but I'd like to make it clear as to why the Inf-sup condition is so much more tricky to deal with than the coercivity condition. Well, part of it was the proof. The proof of coercivity for a bilinear form is typically a slightly more straightforward than proving Inf-sup, this Inf-sup condition, this Inf-sup condition holds. And the second thing that I've also mentioned already is that even though maybe we can prove in the infinite dimensional setting that a bilinear form and hence a partial differential equation is well posed, if we require Inf-sup, then that does not necessarily mean that also a finite element approximation of that problem is well posed. And that's something that I would like to first elaborate on a little bit more. And specifically, I would like to make the distinction between Inf-sup and coercivity here. So the coercivity estimate, or the coercivity requirement, was that, well, this inequality is true for all functions v in our function space capital V, right? So in most of our problems, we're always talking about h1 or h10 for our function space. So this is saying that if I substitute the same function in both slots of my bilinear form, irrespective of what that function may be, as long as it's a function in this function space, then the result of this operation, which will give you a number, is always going to be larger than or equal to the norm of that function squared multiplied by that coercivity constant. And that constant had to be larger than 0. So this has to be true, or if we can prove that this is true for all functions in H1, then this will also be true if I take a subset VH in a subset of V, calling VH, a subset of V. So if our original problem again involves the space H1 and we're using a finite element mesh of these hat functions, or in multidimensional equivalents of these hat functions, well, each of these functions is a function in H1. So the function space that I'm creating by taking any linear combination of these basis functions is a subspace of V, a subspace of H1, which means that if this coercivity condition holds for all functions in H1, well, then it's also going to hold for our finite dimensional subspace all functions in our finite element function space or finite element approximation space. So that means that coercivity carries over to approximation spaces. So coercivity or let me say coercivity carries over to subspaces, such as finite element approximation spaces. Now the same thing does not hold for the Inf-sup condition, and that's why that's such a hassle. So how can we see that? Well, the Inf-sup condition is more complex, and the way that we read this condition is in two stages, right? We take a function phi, and then we perform the inner operation. We try to obtain the supremum of this equation here, which again just gives me a number. So I'll take the maximum number for any possible choice of w in my permitted space y. And then I'll do this for a new phi. And then I'll do it for another phi and another phi. And I'll do this for all possible phis in that space. Well, maybe that space is infinite dimensional, and that's not something that we can actually iteratively do or something like that. But that's the basic idea, right? We perform this operation for all functions phi, and then we take the minimum of that. And that minimum has to be larger than or equal to some constant gamma, which again has to be larger than 0. So the way that we went about proving this for our example problem of the pure advection equation was that we could actually say, well, this inner operation, I don't know what the supremum is going to be. I don't know what the maximum value is going to be. But if I choose w to be equal to, and in that case that was the gradient of phi, for every possible given phi, I will choose w to be the gradient of phi. Then I get a constant here, which means that, and maybe that's not the largest possible constant. Maybe that's not actually the supremum. But nevertheless, I do get a constant here, irrespective of my function phi. So if I were to perform this operation for all choices of phi, well, at the very least, my constant gamma would be equal to that constant that we computed last time. It doesn't mean that the true gamma is actually that constant, but it does mean that we can find a constant such that this Inf-sup condition holds. It doesn't mean that that's the optimal value, but we can show that the condition holds. So why am I rehearsing that, and why is that important? Well, that train of thought follows the basic idea that we want to find a relation between our test function and our trial function. And depending on the spaces that we choose for x and y, well, no, let me state that the other way around. So that means that that relation must be satisfied for all or must be able to be satisfied for all functions w in y for all functions phi in x. Yeah, so that already indicates that there has to be a very strong relation between the spaces x and y. For every possible choice of function phi, I need to be able to take the gradient, and that gradient needs to lie in y, right, in the function space y. Now, for the original problem statement of the pure advection, we had x was h1 with 0 with that funny boundary condition only on the inflow side, and y was chosen to be L2. So then indeed we could always choose w to be the gradient or the first derivative in the one-dimensional case, the first derivative of a function phi, yeah, by definition of the space H1. Now, if we want to do a finite element approximation of the pure advection problem, then we would also need to choose function spaces for phi and for w, for which we're also able to take any derivative of a function phi in the approximation space for phi, and that derivative of that function needs to lie in our test function space. Now, if that sounds a little bit complex, that's exactly the point. That's not easy. We have to be very careful in our choice of function space, and that's precisely the point. So the conclusion here is that Inf-sup does not carry over to subspaces. Yeah, so we have to be very careful. Care is required when constructing finite element approximation spaces. Okay. Clean this up a little bit. There we go. Okay, so that's pretty much all the theory that I wanted to talk about in this video. Let me now jump to the numerical examples. That was already the end, sorry. Okay, that's the first slide. So again, here we have a one-dimensional advection equation. Not sure if I'm able to. Oh yeah, I was struggling a little bit with making notes here, right? Okay, let me see how this works, how well this works. So this was our one-dimensional advection problem. And in principle, that's a very simple differential equation, right? This is something that you can solve by hand. But again, a finite element method actually struggles with that. For this differential equation with this boundary condition, we get that u is going to be equal to the integral of the cosine of x plus some constant. And that's going to be equal to not control Z here? No, okay, whatever. So that means that u is going to be equal to the sine of x plus a constant, and that constant is going to be 0 due to the boundary condition. And that's the function that we're seeing here already in the graph. That's going to be the true solution. So this is the real solution u. So then our finite or a weak formulation of this problem was to find a function u in the space H1, 0 on the left side, such that the integral of dx of u times, well, that's already showing the punchline here, times v is going to be equal to the integral of force function, in this case the cosine of x, times v. And that has to be true for all functions v in L2. And I'll show you two results. One where I'm using standard linear hat functions for our choice of v and for our choice of u. Yeah, so these are going to be my approximation spaces for v and for u. So that's a standard method, right? And in this case, I'm not allowed to add this last basis function here because of the boundary condition, right? Because of this condition here. So that's going to be the first method. That's the naive approach, right? I'm just going to use standard finite element technology for trying to solve this problem. And if we do that, we get this result, right? We see in general very chaotic behavior. It's trying to follow the pattern of the sines of the cosine, or the sine, sorry. But it's undershooting, it's overshooting, it's not smooth, it's not really giving a very clean solution. And if we're dealing, for instance, with concentration, so we're doing the advection of a concentration, then it's actually quite important that we have certain maxima and minima requirements, that those are satisfied. Concentrations are not able to be larger than 1 and not smaller than 0. And if we get concentrations that are outside of those bounds, so either larger than 1 or smaller than 0, this might actually mess up a lot of the future analysis, right? Such requirements are quite important, and clearly that's not satisfied here. Now, why is that? Again, following the analysis from before, we required Inf-sup, which meant in this case that for every choice u, for every function u, we want to be able to choose a v that is going to be equal to the derivative of u. Now, if both u and v live in this space of continuous functions, right, these are all continuous functions, but the derivative of u is going to be a discontinuous function, right, on each element on the left, it's going to be positive, and it's going to be positive, and on the right is going to be negative. So there's going to be a jump here, but in this space I cannot obtain a function that looks like this. So not for every function u, and actually more specifically, not for any function u, I can take the derivative, and that would be something that the function v would be able to take as a shape, yeah? Because we're again using the same spaces for u and for v. So that gives me then the alternative choice. So this is going to be u and v are both going to be equal to that. Now the alternative choice is that for u, I'm going to be using that choice, and for v, I'm going to be choosing, well, precisely the function space of the derivatives of these functions. So what do those look like? Well, that's going to be a positive here and a negative here. And then for the next element, I'll use a positive function here and a negative function here. And for the next element, etc., etc., etc. And actually that space is spanned by a discontinuous Galerkin function space, is what we call that. Something that we'll actually also spend quite some lectures talking about. So these are discontinuous functions from element to element, and actually piecewise constants. So if I now use my trial function space, my solution function space, to be the standard CG1 space, the linear basis functions, piecewise linear, continuous basis functions. But for my test function space V, I use a DG0 space, discontinuous Galerkin space with zeroth order, meaning piecewise constants. And then I get a solution that looks like that, right? That's the green line here. And we see that we get a very good result. Actually, you'll be able to prove that you get these nodally exact solutions. That's not something I want to do, though, in this. Maybe something that we'll get back to towards the end of the class, but for now, I don't think that's important to emphasize. The point, though, being that you do get a very good result now with a method like that. And that is a Petrov-Galerkin method, right? Because we're using a different function space for the test functions and for the trial function. And one particularly important thing to note here is that there are no overshoots and undershoots, right? So if our simulation is so sensitive to overshoots and undershoots because, well, for instance, we're dealing with a concentration, or another example would actually be a density, that you can't get negative densities, of course. So it's important that we satisfy certain maximum and minima requirement, and that's the case for this green line. Okay, and if I overlay those two results, then you clearly see that with the Petrov-Galerkin method, we get a much better result. Okay, well, this is obviously a very easy example here. We have a one-dimensional case, something that we can solve by hand. Let's try a hand at something that's slightly more complex. And this is the problem that we've seen already a couple of times, but that falls very well into the picture that we're trying to paint right now. This is the lid-driven cavity problem for the Stokes equation. And again, the Stokes equation was another equation where we couldn't prove coercivity, and rather we have to rely on the Inf-sup requirements. And as I think I've shown this before twice already, so the point here is that the spaces for the pressure and velocity are in principle independent of one another. You could choose different spaces for these two solution fields, for the velocity solution field and for the pressure solution field. But depending on our choice, and we'll get back to what these choices mean exactly, but depending on the choice of function spaces for those two fields, you get wildly different results. And here on the top I have a couple of examples of different types of elements. And again, we'll get back to what these graphs actually try to mean, what these illustrations of elements actually mean. But for now, the point is only that depending or for different choices of these elements, we get very different results, like the ones in the bottom. And some of them are complete garbage. The one all the way on the right is complete garbage, right? The pressure field and the solution field are both very, very poor. And then for other ones, we get slightly better results, like the second one from the right. But actually, if you take a closer look at that solution field for the pressure, you also find that you get these strange oscillations, which is called a checkerboard pattern. We'll get back to that as well. Even though the velocity field is still kind of okay. Now, the third one from the right, the velocity field is sort of okay, but the pressure field is again very poor. And the one all the way on the left, that's the only one that has a good solution, both for the pressure and for the velocity. Yeah. So the point being again that since we're not able to rely on coercivity, but rather we have to rely on Inf-sup, we have to be very careful in our choices of approximation spaces. Now for the advection, the pure advection problem, there was care in taking a different space for the test and the trial functions. And in the Stokes equation here, it's taking care, or we have to take care in proper choices of spaces for the velocity and the pressure. Right, so and we'll actually use the same spaces for the test functions. Okay, so these are two benchmark problems. Now the last one that I want to talk about is something that I'm actually working on right now, and this is something that we're doing with collaborators who have much stronger industry ties than I typically have in most of my research. This is going to be about friction surfacing, and I'll first show you a little bit of a video of what that is about. It's a pretty hot topic, I would say, within industry. So welding has always been a challenge in the sense that if you weld two pieces of metal together, then you change the properties of the metal at the bond, and you're not able to weld all different materials together, right? So you're kind of limited by what you're able to weld. So for industries like aerospace, where they have to be very smart in the design choices for the materials, or the choices of materials that they want to use for their designs, because they have to be lightweight, they then struggle with the requirement that they also need to be able to weld things, for instance, right? And one new or relatively novel technology in this direction is something that is called friction stir welding. So normally if you weld, you either deposit sort of a molten metal on top of the bond, and that kind of diffuses then onto the two sides, or you just heat the bond a lot and then things melt and you have a lot of pressure and then things also kind of diffuse. But for this friction stir welding, you do something else. So you see an example where they have two pieces, and I think these might be aluminum, and if I'm not mistaken, aluminum is one of the metals that is very difficult to weld. And then in this friction stir welding, what they do is they have a drill bit which they put in between those two plates. It spins at a very high rate, and then they kind of pull that on between the bond. And what happens is actually not that the metals melt. So this is not illustrating a melting metal, but rather a plasticizing metal. So the heat and the friction is producing enough, or the friction is producing enough heat such that the metal starts to plasticize, but not yet melt. And then due to the rotation as well, it's sort of mixing the metals without melting in an interesting way. Yeah, so this is still a relatively novel technique, and there's still quite some open questions. And we're also doing simulation technology, or we're trying to develop simulation technologies for an application like that. And here I have a bit of an overview of what we need for something like that. So sorry, below my picture, what it says here is that these are the main equations, and we're solving for velocity and stress. Okay, I'll get back to that in a second. First, what do we see on the left here? Well, this is sort of a simplified drawing of the thing that we want to simulate. In this case, we're not yet talking about the welding. We're talking about friction surfacing, which is so far just about depositing a metal on a substrate. And again, by spinning this stud is what it is called. The stud, spinning it at a very high rate, such that the heat here is sufficient to produce a plastic flow, and that plastic flow then gets deposited on the substrate to produce this deposited film. Now, secondly, it will also sort of curve upwards. That's producing this flash, and if we look at a cross section here, then that's what we see, right? So part of the metal is plastically flowing into the deposited film, and part of the metal is plastically flowing into the flash, and at the same time the stud is moving to the right, right? That's why we have this deposited film on the left here. Okay, so now how do we go about modeling something like that? Well, first of all, we have to obtain the relevant physical description or the relevant mathematical description of the physics. So I'm showing you this in a class on fluid mechanics, even though this is clearly a solid mechanics application. I've said a couple of times that I don't really see much of a distinction per se. It's really just about the equations that we're dealing with, and we obtain the same. We observe the same issues in certain cases for solid mechanics as we do for fluid mechanics. In this case, that is very relevant because the way that we're describing this problem is from an Eulerian perspective. So you should think of this stud as rotating at a very high amount of RPM, rotation per minute, and at the same time it's pushing down. So material is spinning and pushing downwards, and it's flowing in this direction. So doing this in a Lagrangian sense, like the classical sense of treating solid mechanics problems, you would have to attach your finite element net, your mesh, to the material, which is spinning at an extremely high rate, and which is then also being completely pulled apart and flows into different sections, right? So doing something like that in a Lagrangian setting where we attach the mesh to the solid would not work. We would be pulling our mesh apart, and in general that's would be a very non-robust and very tedious approach to modeling this. So rather what we do is we take an Eulerian perspective, and what I'm doing here is that I'm taking the relevant or the interesting part of this the complete domain. So this is just a cylinder here, and I'll keep my mesh now fixed, so that's going to be a fixed cylinder, and I'll actually have the solid material move through that mesh. And as it's moving through, it's developing stresses, and these stresses should be high enough to produce a plastic flow, and then it will flow out to different sides, either at the bottom or on the left, whatever would happen in reality, hopefully. So now we have an Eulerian perspective, even though we're dealing with a solid mechanics problem, right? So that's, I think, is a very interesting example of why the theory that we're discussing in this class extends beyond pure fluid mechanics. So to give you a bit of an idea of the equations involved here, we have a balance of momentum. So we have a derivative of the velocity, which is balanced by the divergence of the stress field with the density, of course. So this is F is m times a, effectively. But now, due to this Eulerian perspective, we have this additional term here, right? This is the advective term, the advective nonlinearity. Actually, it's the same term that you also get in the Navier-Stokes equation, and that is a term that you only obtain due to this change in reference frame. So that's the balance of momentum. And we have a constitutive law. We somehow have to relate the stress to, in this case, the velocity, where we have just an elasticity tensor. Now, for those of you having taken a couple of classes on continuum mechanics, this is the Baumann time derivative. We have to choose a certain time derivative that is objective. I'm not going to go into these details. Just want to show you some equations. So you have some expressions for that. And again, there's a v dot gradient sigma term involved here. That's the same term effectively as the one up here, coming from, again, the fact that we're dealing with an Eulerian reference frame. Well, these are the kinematic relations, not too important for what I want to say here. And then lastly, we have some viscoplasticity relations here that kind of go into dVp here, viscoplastic. Yeah? This is just a von Mises plasticity relation, but now in a viscous sense, in the sense that it's not going to be independent of the rate at which you apply the stress. And normally if you do like a static analysis of plasticity, then you try to project onto this plane of permitted stress states, and that kind of assumes that we're dealing with an infinite amount of time such that it can settle. In this application, it's precisely the dynamics that are important, so we don't want to assume sort of a quasi-static. We don't want to assume that, and that's why the viscosity sort of plays a role here. So plasticity is allowed to flow. We're interested in the temporal response. So what does a simulation result like that look like? Well, I performed one simulation on a relatively coarse grid, and then I got something along these lines, where from left to right I'm increasing the spin rate at the top over time. And I think at some point after this time step, I'm also starting to press down. So you get also an additional stress concentration here. So the color here is indicative of a total amount of stress in the product of the stress tensor with itself. And the arrows indicate the velocity. Now, I think I scaled the arrows with a factor of 1,000. So the arrows should be 1,000 times larger with respect to the geometry here. Yeah, again, this is spinning at a very high rate. Okay, so this looks sufficiently all right, at least for an initial computation is what I thought. And now, clearly, this is not entirely optimal yet. We see some mesh dependency here, so let's try and refine. And that's when I kind of ran into problems. So, yeah, actually, one last thing that I want to say here is that I have two independent fields. Or two fields that I'm solving for. I have the velocity field and the stress field, and I'm solving for both, right? So I'm not, typically in the way that we handle solid mechanics is that we write the stress in terms of the velocity and then we substitute that into one another. That's one approach, but I'm using here more of a mixed approach where you're solving for both the velocity and the stress. Okay, so then I started mesh refining, and if I do that, then on this slightly finer mesh, I get a solution like that. Okay, that looks a bit smoother. But if I look a little bit more careful, then I what's going on here? Sorry, here. Then I found that I have some strange stress concentrations at some location, at some nodes in my mesh. And if I then continue in time, then I find that that's actually getting worse and worse and worse and worse, and at some point I just get results that don't make a lot of sense anymore. Right, so this is an example case where these instabilities do indeed spoil the results of an industry relevant simulation. So then again, we have to think about where do these instabilities come from. We're dealing with a nonlinear problem. We're dealing with a problem that has this advective term. But I'm also dealing with a problem that is of a mixed nature. And the mixed nature means that we have two different solution fields that we're solving for at the same time, sigma and v. So that's a problem very much of the same sort as the one here, the velocity and pressure. And if we solve for two different solution fields simultaneously, then we typically can't prove coercivity anymore, and we have to rely on Inf-sup, which in this case also means that we have to be very, very careful in our choices of approximation spaces for V and for sigma. Now, this is actually something that I have not solved yet, so I can't show you the answer yet, but that's also what I think is interesting here. This is still ongoing research, and we're trying to figure out how to stabilize formulation like this. Yeah, so everything we're doing in this course is not pure theory without any practice. This is a very relevant example case. And precisely the things that we're talking about in this course apply to something like that. And those are also the things that you have to think about as a computational analyst. Where do these instabilities come from? And how do I go about solving those? So depending on how this research progresses, if I get some nice results in the next couple of weeks, then maybe I'll show these again in a future video. Okay, I think that's all that I wanted to show in this video. Again, get some simulation results showing that that we're not only just doing theory, but this is has a lot of practical relevance. So I hope that was interesting for you as well. In the next video, I'll go back to the theory, but I'll try to kind of balance that a little bit, showing simulation results and theory one by one. Okay, thank you for your attention.